Alright, hello guys. Today we're going to be talking about work. So the work is defined in physics as the transfer of energy caused by a force that moves along with the body that it acts on. So just to understand this a little better, let's have a look at the equation for work and then just hop right into an example so we can get a better understanding of how work works. So the equation for work is W, which stands for work, is equal to F dot D. Now you notice if you looked at the equation for force last time, we just used MA to signify M multiplied by A. This time we have a dot in the middle, and that dot's actually very important because it means that the force and the distance over which the force is applied have to be parallel. It's known as a dot product. And to understand this, let's just have a look at this first problem. So it asks us how much work is done on the box if it's pushed with 3 newtons for 3 meters right. All right, so let's look at our equation. We have W equals F, and since the dot is a little harder to get typed, I'll just use the asterisk to represent it, F dot D. In this equation, our force is 3 newtons, and we see that the box starts off right here at 0 meters and ends up here at 3 meters. So it's traveled a distance of 3 meters. That gives us, when multiplied, a work of 9 Newton meters. And one thing I also want to point out is that Newton meters is actually equivalent to joules. So 1 Newton meter is the same as 1 joule, and that's the unit for energy. So we can see that the amount of work done on the box is 9 joules. That also makes sense because work is a transfer of energy. So this means that 9 joules of energy were transferred to the box through this force. Now let's get into a little bit of a tougher problem. You can see I've already drawn out the free body diagram for it. So the problem is how much work is gravity, specifically gravity, doing on the box in this same situation? So everything's the same. We still have 3 newtons being applied in the rightwards direction while the box moves right for 3 meters. All right, so let's get everything set up. We have W equals F dot D. I have no idea what caused that. We'll go with it for now. So we have a force of how much? Well, you'd think it's 3 newtons, right? But if we look at our free body diagram, 3 newtons is actually our force applied, our Fa right here, whereas gravity is this Fg. So we don't actually know how much Fg is. So then how do we solve this problem? Well, we solve it not by using an equation, but rather by analyzing the problem. Let's think about it. If gravity is acting straight down and the box is moving directly to the right, then is the force of gravity being applied parallel to the direction the box is moving? Well, of course not. It's being applied perpendicularly. So the force of gravity can't be doing any work on this box in this situation. Now let's look at a third problem. This one, just a little bit different from the last one. So we have our physics man from the last problem pushing on a wall with 10 newtons. The wall doesn't budge. It's very important. So we ask, how much work is the man doing? Man here. Typos. Wow. So once again, let's consult our equation. F equals F dot D. All right, so far so good. W equals F, our force, 10 newtons. Then we come into a slight issue. What's the D? What's the distance? We have no reference. Well, think about it. It's a wall. Is it going to move? Of course not. And if the problem's not specifying that it moves, we can assume that the wall is stationary. So 0 meters. All right, well, we know from our math class that anything times 0 is always 0. So the work is actually 0 Newton meters or W equals 0 joules of work. Physics is a cruel subject. He could be pushing on that wall with 1,000 newtons, 10,000 newtons. He would still be doing 0 work. So hopefully that helps you understand work a little better and some of the pitfalls that you might fall into when trying to solve some of these problems. And I hope to see you in the next class. Thank you.